Welcome to this explainer. Look, if you're a process engineer or a formulation scientist in the coatings industry, you already know that efficiency and batch consistency are, well, literally everything. So today, we're bringing you some serious, actionable B2B manufacturing insights. Think of the kind of high-level process optimization you'd usually only see from industry giants like Momentive or Dow. We're going to take some pretty complex chemical engineering concepts and translate them into straightforward strategies you can take to your plant floor right now. Let's get into it.
Okay, let's kick things off with a classic interview question. It's one that actually reveals a super common and honestly incredibly costly industry myth. How much does grinding temperature really affect pigment dispersion? You know, a lot of newer engineers might tell you, temperature's just a background variable, it's just a minor environmental fluctuation, nothing to lose sleep over. But here's the thing, treating heat as an afterthought, that is exactly why so many batches completely fail or just lack consistency.
Think about it. During the grinding process, you're pumping massive amounts of mechanical energy into your system. But thanks to the law of conservation of energy, only a tiny fraction of that energy actually goes into breaking apart those pigment agglomerates. The vast majority of it converts straight into heat. And today, we're going to show you exactly why this temperature spike is actually the master switch of your entire formulation. I mean, it completely alters your fluid's physical and chemical properties.
So, here's a quick look at our agenda for today. We're taking a micro to macro journey. We'll hit the hidden temperature trap, the 3 stages of dispersion, the viscosity trade-off, Brownian motion and stability, the dispersant balancing act, and finally, finding your optimal zone. All right, section 1, the hidden temperature trap. So when you're grinding pigment, that immense mechanical energy is drastically altering the thermodynamic reality of your slurry, right in real time. We are not talking about a cute 1 or 2 degree shift here. In high-intensity milling, we're seeing temperature spikes that can easily hit 30 to 40 degrees Celsius above your baseline. No way is that just background noise. That is a massive thermodynamic shift that hits your viscosity and surface tension directly. It literally penetrates every single stage of your process. Which brings us to section 2. 3 stages of dispersion. Now, every successful batch has to progress through these 3 specific steps sequentially. First, you've got wetting. That's replacing the air and moisture trapped on the pigment with your liquid. Second is breaking, where mechanical energy physically shatters those clustered particles. And third is stabilization, where your dispersants lock onto those newly freed particles so they don't just clump back together. But here is the kicker. Temperature is quietly in the background, rewriting the rules for every single one of these steps. Let's look at exactly how in section 3, the viscosity trade-off. Okay, quick definition for us. Yield stress. Simply put, it's the minimum mechanical force you need to push a stationary fluid into a state of active flow. Well, when your temperature spikes, it accelerates molecular movement, right? This pushes the molecules farther apart and severely weakens the van der Waals forces that are trying to hold them together. The result? Your fluid's yield stress and overall viscosity plummet. And I mean, they drop exponentially, not linearly. Exponentially. And this creates a huge contradiction. On the plus side, lower viscosity and lower surface tension mean your liquid flows like a dream. It gets into all those tiny gaps in your pigment and massively speeds up the wetting phase. Sounds amazing, right? But wait. On the flip side, that lower viscosity completely destroys the shear stress in your mill. You absolutely need that thick, viscous friction to actually crush and tear the particles apart. So basically, heat helps you wet the pigment, but it actively sabotages your machine's ability to grind it. It's a total catch-22. Let's zoom in even closer on this. Section 4, Brownian motion and stability. We've got to talk about Brownian motion. This is that continuous, completely random movement of microscopic particles in a fluid, driven by unequal collisions with the fluid molecules themselves. As your temperature goes up, the kinetic energy of the whole system just goes off the charts. Your fluid basically turns into a chaotic, high-speed bumper car arena for your pigment particles. And once again, we're looking at a paradox. Sure, on one hand, that extra chaotic kinetic energy can give you a little assist in tearing apart loosely bound clumps of pigment, but honestly, it mostly acts as a total saboteur. The collision frequency goes absolutely through the roof. Those perfectly separated particles are moving so fast that they slam into each other, bust through their protective barriers, and just fuse right back together. You are literally watching your hard work undo itself because the system is just too hot and too chaotic. So how do we stop that? Section 5. The dispersant balancing act.
Getting a dispersant to actually anchor onto a pigment particle is a purely thermodynamic process governed by Gibbs free energy. Generally speaking, dispersant adsorption is an exothermic process. That just means as the dispersant locks onto the particle, it naturally releases heat and lowers the system's entropy. Basically, it moves the system from a state of chaos into a nice, stable state of order. But here is the crazy twist. Higher temperatures actually speed up the kinetic rate of diffusion, so the dispersant rushes through the liquid super fast to coat those freshly broken particles. Awesome, right? But thermodynamically, because adsorption naturally releases heat, forcing excess heat into the system pushes the equilibrium right back in the opposite direction. If it gets too hot, the Gibbs free energy balance shifts, and you literally start boiling the protective dispersants right off the pigment. They fall right off, leading to massive desorption and instant reaggregation.
So how do engineers actually fix this? Section 6, Finding Your Optimal Zone. Take a look at this matrix. It perfectly illustrates how every single time a temperature increase solves a kinetic problem, bam, it simultaneously creates a thermodynamic failure point. It helps wetting, but evaporates your solvent. It improves flow, but absolutely kills your shear breaking force. It speeds up your dispersants, but then rips them right back off the particle. You just can't maximize one variable without completely punishing another. And that brings us to the absolutely crucial takeaway of this explainer. There is no universal magic number for temperature, period. You cannot just set your chiller to 35 degrees and assume you're perfectly optimized. Temperature is a living, dynamic balance that is highly specific to your exact formula, your resins, and your dispersants. Finding that optimal zone means you have to map out these thermal trade-offs for every single unique product line on your floor.
So, I want to leave you with this to think about. Look back at the batches that failed quality control last month. Take a hard, honest look at your process controls today and ask yourself, is treating temperature as an afterthought the real reason behind your batch inconsistencies? Are you actively managing the master switch, or are you just letting the machine dictate your thermodynamics? Thanks so much for joining me for this explainer, and I really hope this helps you lock in those optimal zones moving forward.